In 2020, I started college as an engineering student. It was pretty crazy. I had to do more work than I ever thought I was even capable of doing. So much math, physics, chemistry, Excel, and it was amazing. Well, not really, but at the same time it was. Or it wasn't? The bottom line is, I was in my element. My whole life I've been a nerd, and never did I feel more at home than I did at Purdue. Which left me with a rather unfortunate dilemma come May. I had to go home. Don't get me wrong, I love my family, and I was certainly excited to get away from the non-stop grind of school, but I was worried that I'd be bored. You see, at college, I was constantly able to express my creativity through my projects, my friendships, and my classwork. At home, I had no 3D printer, no soldering iron, and no ultra-nerdy friends. And by the way, to all my Purdue friends watching this, that's a compliment. So I decided I was going to make something. My first thought was that I'd make a go-kart swerve drive, but then I remembered I'm broke. So I moved on to plan B, a robotic something. First, I thought about making a robotic dog, but then I remembered I'm broke. So I moved on to plan B.5. B.5 is that? I'd make a robotic dog with one leg, except the leg would be upside down, hold a Sharpie. Yeah, it's a robot arm. Okay, I was gonna make a robot arm. Robot arms are great because they're cheap, relatively, involve a lot of fun technical challenges, and simple enough to make in the span of time I have this summer, which is basically just a few hours a day in between my horrendously long work hours. But you may be thinking, Dash, you already made a robot arm. Well, you'd be correct, but you may also recall that it drew as well as a toddler. Now, for some people, that would be good enough, but not me. You see, I'm a professional engineer. So, this time, I decided I'd get real. Step one was, of course, modeling the arm and planning it out. In early May, before I had a job to suck up all my time, and no money to spend on robot parts, I decided to get started from scratch designing the arm so that come June, I could buy the parts and make it. My first iteration was absolutely gorgeous. It used custom cycloidal actuators to get its torque and mitigate that backlash. However, this design wouldn't do. It was made up of about 6 times 10 to the way too f***ing many parts, and as the US Navy used to say, keep it simple, stupid. My second design used gearboxes made by someone else, so that I didn't have to make them, saving me massive amounts of time. This concept had a different issue, however, one that was simply insurmountable. It was hideous, and probably unstable due to the fact that it had no support of bearings. However, I acknowledged that I would not be able to make it work if I didn't kiss. So I hunkered down and I designed this, the V2 of the V2 of the V2, and it was perfect. Unlike the arm of yore, it used stepper motors, special precise motors used on CNC machines, 3D printers, and more because they're, well, precise. Stepper motors have an issue, however. They don't know where the they are, so you have to tell them. And in my case, I decided to do so using a magical technology called Hall effect sensors. These bad boys can detect a magnet from a millimeter away, so I integrated them into each joint, along with a teensy tiny magnet. The magnet only triggers the sensor when it's in this exact position. So, when the magnet is detected, the arm knows what angle the joint is at. Precise motors, check. Precise positioning, check. Theoretically, at least. More on that later. With the arm designed, all that was left to do was very reluctantly hit buy. To help me construct the arm and other future home projects, I purchased myself an Ender 3 Pro, very good 3D printer, by the way, some sparkly filament because my sister was at the store when I got it, and a whole swath of tools, and a whole lot of determination. When the parts had arrived and the 3D printing was done, I got to construction. What I thought would be easy, but was actually pretty hard. Before construction starts, however, I thought I'd give you a quick overview of how the arm actually works. So in the base, we have the first axes of the 3 axes, which make this arm a 3 degrees of freedom arm, 3 axes. The base itself is steered by a NEMA 14 stepper motor, which is tensioned on this top plate here, and that's connecting to a belt, which connects to the actual arm itself on the bottom. When that NEMA 14 stepper motor spins, it also spins the entire arm, giving it its first degrees of freedom. Within this bottom piece also is contained the first Hall effect sensor, and in the large pulley there is another magnet, which is how it homes, just like the other joints. Connected to the top of this 80-tooth pulley is the rest of the arm. Directly on top of it you'll find the shoulder joint. The shoulder joint is powered by a NEMA 11 stepper motor connected to a 27-to-1 gearbox. This gearbox gives the motor the torque it needs to move the rest of the arm. Connected to the shoulder assembly is a long brachium section, just like you have in a normal human arm. And at the end of that brachium, you will find the second NEMA 11 motor with that gearbox on it. That is the elbow joint. The elbow itself is currently just a stub because we haven't connected the Sharpie yet, but as I said, you'll see that in the next video. So there you have it. That's how the arm works. Now, let's get to building it and talking about some of the struggles I encountered along the way. Construction actually went relatively smoothly. Everything fit together excellently. I only had to redesign 3 parts, which actually isn't that bad considering that for some dimensions in the modeling phase, I just guessed. One part in particular, the part that interfaced between the shaft and the shoulder and the elbow joint, gave me some trouble. The part itself kept slipping on the shaft because too tight and the part would have to be softened with a heat gun and then jammed into place, causing the joints to be askew, killing the accuracy. But too loose and the arm would wiggle, another suboptimal outcome. The final solution I came up with was this clamp design, which utilized embedded metal nuts and a clamping system to apply pressure on the shaft. This design was the best of both worlds because it was tight enough to avoid slipping and loose enough, when loosened of course, to easily slide onto the shaft. Step 2 was to wire it. My old robotic arm used an Arduino, a 5-volt regulator, and good old servos. And that's it. You don't need anything else to drive servos. Just 5 volts, an analog signal from the Arduino, and that's it. This arm, however, is just a tad more complicated on the wiring front. This arm's powered by a 60-watt 12-volt power supply which jacks into this rat's nest you see here. On these 2 Perma Proto breadboards, you will find 3 A4988 stepper motor drivers, which would actually connect to the stepper motors to power them. On the arm itself, you will of course find all 3 Hall effect sensors, which are also wired straight into this rat's nest. All these sensors and boards are connected to a Teensy 3.2, the brain of the arm. This microcontroller is basically an Arduino Nano on steroids, packing 20 additional digital I/O pins, a much faster processor, and even Wi-Fi. Finally, powering up everything is the same 5-volt buck converter I used to power the servos on the V1 arm, except this time, instead of powering the entire system, it's just powering the teensy and the logic part of the A4988s. Now, it was at this point that I loaded some test code onto the board and clicked go for the first time. I was excited, to say the least. Roll the clip.
There's no code, it's not doing anything fancy, I just wanted to see if it moved, and it moves. Watch this. You saw that, right? You saw it move because it moves. Watch. It moves. It does. It moves. Ready for this?
Due to the increased electronic complexity, there are a grand total of 21 wires tethering the arm to the electronics, as well as about a bajillion more to provide various voltages and powers to all the components. So altering these wires took 7 hours, but then I realized that there was virtually no slack for the arm to move, so I had to extend them all. Twice. And then pack them into this special box which I designed, because I like things to be neat. Step 3 was to get it to move more than it already had. Now that it was wired and constructed, all I needed to do was program it. Since I've been working on this for 6 weeks now, and keep in mind, that's like on and off 6 weeks, I've been pretty busy elsewhere, I decided to stop and make a video detailing how far I'd come, which is what you're watching now. Do temper your expectations, because what you're about to see isn't the final functionality of this arm. In the next video, you'll see a lot more of that. I started by writing some homing code. This code utilizes the magnet sensors in the arm to home. It works by moving the arm until a magnet is detected, and then recording that position as home for the joint, and of course stopping the movement. There are a few steps in between, but that's the basic idea. Then I wrote some code to move all the joints to a desired angle.
Here I have a little console. It's asking currently for the base angle. Base is currently at 135 degrees. If I set it to 90 degrees, I'll set it to 90 degrees. So I put 90 degrees right into my console. Push enter. Once a shoulder angle, I'm gonna put the shoulder at 70 degrees, and I'm gonna put the elbow at, let's just do 110. Now watch this. And there it goes. So now, as you can see, it's still perfectly level because I did the opposite angle, but the arm has now rotated. And the base has actually not rotated correctly, so I need to fix that. It seems that the rest of it has. The shoulder and the elbow are totally working. So let's just go back to the 135 base angle. I gotta fix that ratio or something, but the shoulder angle will go back to 90. We'll go back to 90. As you can see, it will go back to its original position. It's now done that. So now it's right where it started. It's right where it homed. I need to fix the base, but it's working pretty well.
And that's what I've got for you so far. This project has obviously been an arduous one, and a time-consuming one. I don't get many views on these videos, but I enjoy my projects too much to keep them to myself. So please do like, subscribe, and share if you enjoyed the video. And of course, stay tuned because a part 2 is on the way very, very soon. By very, very soon, I mean by the end of August.